Hello, this is John Miares, and in this video, we're going to be looking at several concepts which are an extension of what we've already been doing so far in section 6.1 and 6.3, but now apply them to radian measure. We're also going to look at how we can evaluate trigonometric functions of what we referred to earlier as quadrantal angles, those whose terminal sides fall on either the x or y axis, which would make the construction of a reference triangle impossible. And we're going to explore a concept called the unit circle, which allows for an alternative approach to dealing with these trigonometric functions. At the beginning of this course, we did a review of circles. The most basic of those circles were the ones centered at the origin. This thing we're calling the unit circle is a circle that is centered at the origin and has radius 1. It has the equation x squared plus y squared equals 1. Here is a graph of this circle. As a reminder from our earlier studies, every point on the graph of this circle is a solution to the equation for the circle. So one of the first things we're going to look at is a review of how to verify that a point might actually be on this circle. For this exercise, we want to determine if the following points are on the unit circle. So what we'll need to do is substitute the x and y values given into the equation x squared plus y squared equals 1 and see if the solution does come out to equal 1. For the first one, we'll take negative 24/25 squared plus negative 7/25 squared. Squaring these out gives us 576 over 625 plus 49 over 625. And adding those together will give us 625 over 625, which equals 1. Let's pause the video for a bit to see if you can try the next couple on your own. For the second example, we'll take 5/7 squared plus negative 2 square roots of 6 over 7 squared. Squaring out the first fraction, you get 25 over 49. And with the second fraction, you get, well, you have to first square the negative 2, which gives you positive 4. Then you take the square of the square root of 6, which gives you 6. And 4 times 6 equals 24. This gives you a final fraction of 24 over 49, which when we now add the two fractions together, will get you 49 over 49, which equals 1. For the last example, we'll do the same thing, squaring each of the terms. The negative square root of 11 over 6 squared will become positive 11 over 36, while 5/6 squared becomes 25 over 36. Adding these together will give you 36 over 36, which equals 1. A couple of things to note. Be careful when you are squaring the negative numbers on your calculator that you're sure to actually include the negative sign inside the parentheses before doing your squaring. Remember, when you're squaring something, the result should always be positive. So if you get a negative answer when squaring something, you know you did something wrong. Secondly, all of these points, when plugged into the equation, happen to come out to equal 1. This means that they must all be points on the circle. If you look carefully on your calculator or on a graphing app like Desmos, we can locate all of these points on the circle. Now let's try something a little bit different. Suppose you are told that a given point is on the unit circle and you are given one of the coordinates, but not both of them, and you want to find out what the other coordinate of that point should be. Here are a couple of examples you should try on your own. In the first one, you're told x equals -15/17 and you want to solve for y. In the second one, you're given y equals -2/5 and you want to solve for x. To do this, you'll plug the given numbers into the equation x squared plus y squared equals 1, then solve for the missing variables. Why don't you pause this video and give these a try on your own? All right, so in the first example, if we take -15/17 squared, you're going to get 225/89. In order to solve for y, we're going to have to move it over to the other side, but in order to combine it, we're going to need to get a common denominator, so we turn the 1 into 289/289. Subtracting 225/289 from the 289/289, you're going to get y squared equals 64/289. Taking the square root of both sides, you're going to get y equals plus or minus 8/17. Now, we don't have our final answer yet. The decision on whether we want to use the plus or the minus will be dependent upon what quadrant the point lies in. In the first example, we want the point to be in quadrant 2. And in quadrant 2, the y values are always positive. So what we'll have here is y must be positive 8/17. In the second example, we're doing the same thing. So we've got x squared plus -2/5 squared equals 1. Squaring out the fraction makes this x squared plus 4/25 equals 1, which we must convert into 25/25 in order to combine the fractions. Subtracting the 4/25 to the other side gives x squared equals 21/25. And when we take the square root of both sides, we get x equals plus or minus the square root of 21/5. As far as whether we're going to use the plus or minus sign, we see that we're in quadrant 4. And in quadrant 4, the x values are going to be positive. So our final answer is going to look like positive the square root of 21/5. Again, if we want to double check our results, we can try plotting the given points, since we know every point on the graph is a solution to the equation. Using our graphing calculators or some other graphing utility, we should be able to see where those points lie on the graph. Now, in section 5.1 and 5.2, they explore the idea that if we are working with angles in standard position, and if we were to focus on the point where the terminal side of the angle intersects the unit circle, then the sine of the angle will reduce to simply the y coordinate, and the cosine of the angle will reduce to simply the x coordinate of the point of intersection. This is because in this unit circle, the hypotenuse equals 1. So y over r becomes y over 1, and x over r for the cosine becomes x over 1. In this diagram, we see that situation labeled here. The terminal side of angle theta intersects the unit circle at the point xy. The sine of angle theta is computed as y over r, but if r equals 1, then the sine of theta simplifies to just y. This is marked in blue as the opposite side of our reference triangle, which has length y, which also equals the sine of theta. Similarly, if the cosine of theta normally equals x over r, and in the unit circle r equals 1, then the cosine of theta will just become x. The adjacent side of the reference angle is going to be marked here in green, and it has length x, which will also equal the cosine of angle theta. Also marked on this triangle is the arc subtended between the initial side of the angle and the terminal side of the angle, and that we have marked in red. Because we're on the unit circle, the length of this red arc will equal the angle measure in radians. If you recall, the definition of how many radians would be in an angle is it was the ratio of the arc length subtended by the angle to the radius. Well, if the radius is 1, then that arc length divided by 1 will equal the radian measure. Now, please note that these ideas are essentially the same as what we were working with in previous sections, except now r equals 1. Now, generally, I'm going to be just showing you these representations because they're in the book. And in this section, it's not that critical that you remember this setup because it really is a very specific situation which only applies to when we are working with the unit circle. If you follow along with the strategies that we covered in section 6.3 for evaluating the 6 trigonometric functions of angles in standard position, then you're going to be just fine. But since this is built into the textbook and you're expected to cover part of it, we are going to be looking at this a little bit more carefully. So let's look at an example of this. Suppose I tell you that the terminal side of angle theta passes through the point 0.8, 0.6, and you want to find the sine of theta and the cosine of theta. The first thing we should probably do is verify whether or not this point is actually on the unit circle. So let's plug this into our equation for a unit circle, taking 0.8 squared and 0.6 squared and adding them up to see if they equal 1. Well, 0.8 squared is 0.64 and 0.6 squared is 0.36. Adding these together does give 1. That means that the point is on the unit circle, so let's construct our angle theta in standard position in such a way that the terminal side passes through the point 0.8, 0.6. Then we'll drop a perpendicular to create our reference triangle, just like we did in the last section. We mark the angle theta as shown, and we'll label the sides. The opposite side will be the y value, and we'll have a length of 0.6. The adjacent side will be the x value, we'll have a length of 0.8. The hypotenuse will be 1 because, well, the Pythagorean theorem says so, and because we're on a unit circle, it implies that the radius is 1. Now we'll calculate out the sine and the cosine. The sine of theta, which we know to be the y-coordinate over the radius, or the opposite over the hypotenuse, looks like 0.6 over 1, which we can leave as 0.6, or we can turn into the fraction 3/5. The cosine of angle theta, which we normally compute as x over r, or adjacent over hypotenuse, will be 0.8 over 1, or just 0.8, and we can turn that fraction into 4/5. So again, we see in this particular case, because the hypotenuse equals 1, that the sine value will simplify to just plain y over r, just the y value, and the cosine value will simplify to just plain old x. However, I cannot emphasize enough that if this wasn't on the unit circle and the hypotenuse did not equal 1, then you would need to use the rules of SOHCAHTOA, or the rules y over r, x over r, to find the sine and cosine of this angle. Next, we're going to look at quadrantal angles. We introduced quadrantal angles in the previous sections, defining them as angles in standard position whose terminal side falls on either the x-axis or the y-axis. These would include 0 degrees, 90 degrees, 180 degrees, 270 degrees, or any angle coterminal with those. Since a reference triangle cannot be constructed with these angles, this is a case where we will have to use the x, y, and r definitions of the 6 trigonometric functions to evaluate these based on the terminal points rather than setting up reference angles and reference triangles. Here, working with the unit circle will actually make these computations much simpler. Let's look at how we might compute the sine, cosine, and tangent of some of these angles. We'll start with 0 degrees, then go to 90, then 180, then 270. Every time we've talked about finding sine, cosine, and tangent of some angle theta in standard position, we've had to find some point on the terminal side of the angle. And this case is no different. For a 0-degree angle, the terminal side will fall on the positive x-axis. So we could pick any point on the positive x-axis to use as a reference point. In this case, the simplest point to pick is going to be the point 1, 0. This is because the point 1, 0 is only 1 unit away from the origin, which will make our computations of sine, cosine, and tangent quite simple. The sine of 0 degrees will be y over r, which reduces to 0 over 1. The cosine of 0 degrees, x over r, becomes 1 over 1, which is 1. And the tangent of 0 degrees will be y over x, or 0 over 1, which reduces to 0. For a 90-degree angle, the terminal side lies on the positive y-axis, so we can pick any point on the positive y-axis as our reference point. So for simplicity's sake, we're going to choose 0, 1, which again will only be 1 unit away from the origin. The sine of 90 degrees, y over r, becomes 1 over 1, or just 1. The cosine of 90 degrees, now x over r, is going to become 0 over 1, or just 0. The tangent of 90 degrees, y over x, becomes 1 divided by 0, which is undefined. Now, for those who are wondering why this is undefined and why it doesn't equal 0, remember, division is the opposite of multiplication. 1 divided by 0 doesn't equal any real number because no real number multiplied by 0 can ever equal 1. That's not the same as when we took the tangent of 0 degrees and got 0 divided by 1 equals 0, because 0 times 1 equals 0, and that's fine. But nothing times 0 equals 1. So 1 divided by 0 can't equal any real number. Let's look at 180 degrees. This angle's terminal side falls on the negative x-axis, so the point that we pick is going to be negative 1, 0 on the terminal side, which will again will keep our r value equal to 1. The sine of 180 degrees will be 0 over 1, which is 0. The cosine of 180 degrees will be negative 1 x over positive 1 r, which equals negative 1. And the tangent of 180 degrees will be 0 over negative 1, which becomes 0. Finally, let's look at 270 degrees. The terminal side falls on the negative y-axis, so for simplicity, we're going to pick the point 0, negative 1. The sine of 270 degrees will be negative 1 over 1, or just negative 1. The cosine of 270 degrees will be 0 over 1, which is 0. And the tangent of 270 degrees will be negative 1 over 0, which again is undefined. While it is a good idea to memorize these, it may be easier simply to remember where the terminal sides lie so that these values can be derived pretty easily as opposed to memorizing all the individual values. Also, say we were working with quadrantal angle whose measure is bigger than 360 degrees, or perhaps is a negative measured angle. So long as we can determine what axis the terminal side falls on, or if we can figure out what angle we're coterminal with, then evaluating the trigonometric function won't be that hard. Let's look at a few of these. Suppose you were asked to evaluate the tangent of 450 degrees. 450 degrees is 90 degrees past 360, and the measures start back over at 360. So we can say that the tangent of 450 degrees will be the same as the tangent of 90 degrees, which according to our table above will be undefined. Let's try a different one, maybe one that doesn't involve sine, cosine, and tangent. Suppose I'm asked to find the secant of 540 degrees. We first need to figure out which of these primary angles 540 degrees is coterminal with. Subtracting 360 from the 540, we find it will line up with 180 degrees. Now, we need to remember that the secant is the reciprocal of the cosine. So what we will need to do here is take the reciprocal of the cosine of 180 degrees. Since the cosine of 180 degrees is -1, then the secant of 180 degrees will also be -1. Here's a couple you can try on your own. Pause the video and see if you can determine what the cosecant of -90 degrees and the cotangent of 900 degrees are going to be. Remember, you'll need to first figure out which of these angles they are coterminal with, then remember which trig ratios are the reciprocals of these. Let's pause the video and see what you can come up with on your own. All right. -90 degrees is going to be coterminal with 270 degrees. And with the cosecant being the reciprocal of the sine, we want to find what is 1 over the sine of 270 degrees. Since the sine of 270 degrees is -1, then the reciprocal is also going to be -1. For the cotangent of 900 degrees, we need to back up a couple of rotations to realize that 900 degrees is coterminal with 180 degrees. Next, we need to remember that cotangent is the reciprocal of the tangent. And the tangent of 180 degrees is 0. So then the reciprocal of 0 is going to be undefined. Now, you could also look at this as -1 over 0, which, if you consider that tangent is y over x, cotangent is x over y, so technically you're dividing -1 by 0, but neither of them is defined, so it doesn't really matter all that much. Before we look at any new examples, I wanted to summarize what we now know about our special angles and our quadrantal angles into a complete table of values. Here is the chart which many will say needs to be memorized, but ultimately, if you can't memorize all of it, there are certain parts that I would suggest memorizing, but then we can leave the rest as things that we can derive. For example, this table shows the values of the 6 trigonometric functions of the 4 primary quadrantal angles, including 0 degrees, 90 degrees, 180 degrees, 270 degrees. The radian equivalent for those angles are also shown: 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians. What might be easier to remember rather than the values in all of those columns is the points that we used on the terminal side of those angles to generate the key values. 0 degrees or 0 radians passes through the point 1, 0. 90 degrees or pi over 2 radians passes through the point 0, 1. 180 degrees passes through the point negative 1, 0, and 270 degrees passes through the point 0, negative 1. From here, if you can remember that sine is y over r, cosine is x over r, and that r for all of these cases is going to equal 1, then the other values can be pretty quickly derived based on their relationship to sine and cosine. For example, one way we can look at the tangent is that it can be computed as the sine over the cosine. Think about it for a second. Tangent is normally calculated as opposite over adjacent. If you look at the sine ratio, that's opposite over hypotenuse, and you divide it by the ratio for the cosine, adjacent over hypotenuse. When you flip and multiply, the hypotenuses are going to cancel, leaving you with opposite over adjacent, which is tangent. As for the others, cotangent is reciprocal of the tangent, secant is reciprocal of the cosine, and cosecant is reciprocal of the sine. This way, if we know the cosine of 0 is 1, then the secant of 0 will be the reciprocal of that, which is 1. If we know the cosine of 270 degrees is 0, then the secant must be undefined because the reciprocal of 0 is undefined. Now, as for the 30, 45, and 60-degree reference angles, I'm going to show you a trick that will help you memorize those lines much more easily. Let's say I'm looking at the line with the sine of theta here, and I'm going to go across the top row from 0 degrees over to 90 degrees, or from 0 radians to pi over 2 radians. You'll see I've got 0, I've got 1/2, square root of 2 over 2, square root of 3 over 2, and 1. There is a bit more that we can do to help look at this pattern. If we go back to our study of sequences from chapter 12, I see that with 45 degrees and 60 degrees, I have the square root of 2 over 2 and the square root of 3 over 2. So I see that I have this expression, this pattern, where I have the square root of something over 2. We could do the same thing with the first expression. Looking at the sine, I could rewrite that as the square root of 0 over 2, which does divide out to equal 0. Similarly, we could take the sine of 30 degrees, which is 1/2, and rewrite that as the square root of 1 over 2. Now, as I read across, I've got the square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and if I look at the value for 1, that could be rewritten as the square root of 4 over 2. So now I have this really cool pattern that shows up when I go from 0, 30, 45, 60, 90. I got square root of 0, square root of 1, square root of 2, square root of 3, square root of 4, all over 2. Now, cosine works backwards. You're starting out with root 4 over 2, then root 3 over 2, then root 2 over 2, then 1/2 becomes root 1 over 2, and then cosine of 90, which is 0, can become root 0 over 2. So now, as long as you can remember these patterns, that the sine of 0 starts at 0 and works its way up to the sine of 90 equals 1, and the cosine of 0 equals 1, and it works its way back down to the cosine of 90 equals 0, and if you can remember which trig ratios are the reciprocals of each one, then you can derive what you want from this table without having to memorize the entire table. Well, now you're probably asking, what do we need to do in the other quadrants? Should we be extending this table to include all of the angles in all the quadrants? Something like 120 degrees, 135 degrees, 150 degrees? Well, you could, but if you can remember the strategies we used involving setting up reference triangles and attaching appropriate positive, negative signs to the side lengths, remember the all skiers take chances pattern, then you probably don't need to go much further than knowing what is on this table right here. Let's look at how we might evaluate trigonometric functions of angles when the angle is given in radians and perhaps isn't one of the ones that's on the chart from the previous slide, but we could set up a reference triangle for. The procedure is very similar to what we did in section 6.3, except the reference angles are going to be measured in radians instead of in degrees, and any measurements that were taken from the nearest x-axis will be in multiples of pi rather than multiples of 180 degrees. The steps aren't any different though. First, we're going to draw a picture of an angle in standard position. Then we'll construct the reference triangle and determine the measurement of the reference angle and reference triangle. Once we have done that, we can label the lengths of the three sides of the reference triangle. If we only know two of the sides, we can use the Pythagorean theorem to get the third. Remember, as we label our side lengths, that the leg lengths may be positive or negative depending upon what quadrant the terminal side lies in, whereas the hypotenuse, or the radius, is always going to be positive. Now let's try some examples. We're going to evaluate various trig functions at these special angles using the strategies discussed on the previous slide and from the previous section. For reference, I'm going to include the two special triangles from section 6.2b, but the diagrams are showing radian equivalents for the 30, 45, and 60-degree angles. Those would be pi over 6, pi over 4, and pi over 3. I'm also including this diagram which shows what the equivalent degree and radian measures are of the quadrantal angles, which will help us figure out what quadrant the angles will lie in as we work our way around the circle. Here's the first couple we want to try. The cosine of 4 pi over 3 and the sine of 7 pi over 4. In the first case, 4 pi over 3, which is 1 1/3 pi, if I turn that into a mixed fraction, is bigger than pi, but less than 1.5 pi. So that's going to place the terminal side in quadrant 3. The reference angle is determined by figuring out how far we are from the x-axis. As we said before, 4 pi over 3 is the same as 1 1/3 pi. So we're 1/3 pi units past the negative x-axis, which means our reference angle will be pi over 3, or 60 degrees. In quadrant 3, only the tangent and cotangent come out positive, so the cosine will be negative. Rewriting this expression in terms of the reference angle, the cosine of 4 pi over 3 will be now the same as the negative cosine of pi over 3, or the negative cosine of 60 degrees. Looking at our 30, 60, 90 reference triangle, we have the cosine of 60 degrees adjacent over hypotenuse is 1/2. So the cosine of 4 pi over 3 will come out to be negative 1/2. But the sine of 7 pi over 4, we first may want to turn the angle measure into a mixed fraction. 7 pi over 4 is 1 3/4 pi. So that is bigger than 1.5 pi, but less than 2 pi, which puts our angle into quadrant 4. The reference angle, well, we're only 1/4 pi away from 2 pi, so the reference angle is going to be pi over 4, or 45 degrees. In quadrant 4, cosine is positive, which means that the sine, SIGN sine, of the sine function, SINE sine, will be negative. So the sine of 7 pi over 4 will be the same as the negative sine of pi over 4, or the negative sine of 45 degrees. If we look at that on our reference triangle, that tells me that my value will come out to be negative square root of 2 over 2. Negative because we're in quadrant 4, square root of 2 over 2 because it's a 45-degree reference angle. Here's a couple that perhaps you can start on your own. The process is the same as far as getting the reference angle and the proper positive and negative sign attached. You'll just need to remember which trig ratio is the reciprocal of which. Go ahead and pause the video to give yourself a chance to try these on your own. So 5 pi over 6, 5/6 pi, is less than pi, but greater than half pi. So that will fall in quadrant 2. Now, the terminal side of 5 pi over 6 is only 1/6 pi away from the negative x-axis. So the reference angle will be pi over 6 radians, or 30 degrees. In quadrant 2, the sine function will be positive, which means the cosecant, its reciprocal, will also come out positive. So the cosecant of 5 pi over 6 will equal the cosecant of pi over 6 radians, or equivalently, the cosecant of 30 degrees. Looking at our reference triangle, knowing that the sine of 30 degrees equals 1/2, then the cosecant is going to equal 2 over 1, or just 2. Now, 9 pi over 2, if I turn that into a mixed fraction, divides out to 4.5 pi, which means that you're going 2 full revolutions, which would be 4 pi, and then an additional half pi, or 90 degrees, past the second revolution. This means we have a quadrantal angle. And so when we're asked what quadrant it's in, technically the answer is none of them. However, what we should probably make a note of is that the angle falls right between quadrants 1 and 2, because that might help give us some clues as to how to interpret the sign. The reference angle, we could say, is 90 degrees, or pi over 2, even though I can't construct a reference triangle out of this. It's still going to be able to be used to evaluate the function. As for the positive and negative sign, we could say this. The 90-degree angle falls right between quadrants 1 and 2. In quadrant 1, cotangent is positive. In quadrant 2, cotangent is negative. So it seems reasonable that right in between, that the answer should be neither positive nor negative. That really limits us to two choices. Either the answer will be 0, or the answer will be undefined, because those are the only two values in our table that are neither positive nor negative. So the cotangent of 9 pi over 2 is going to be the same as the cotangent of pi over 2, which is the same as the cotangent of 90 degrees. 90 degrees passes through the point 0, 1. So if you were looking at the tangent, y over x, you would get 1 over 0, which would become undefined. But if you look at the cotangent, x over y, you would do 0 over 1, which means the measure of the cotangent of 90 degrees is going to be 0. Let's try a few more. And again, why don't we pause the video for a bit to try a few of these on your own? All right, here we go. For negative 3 pi over 4, we are rotating in the negative direction. And 3/4 pi is less than a half revolution, but so we should end up in quadrant 3. The terminal side of the angle is only a 1/4 pi radian away from the nearest x-axis, so the reference angle will be pi over 4, or 45 degrees. Meanwhile, we know the tangent is going to be positive in quadrant 3, so we can rewrite this expression as the tangent of negative 3 pi over 4 as being equal to the tangent of pi over 4, or the tangent of 45 degrees, which according to our reference triangle, opposite over adjacent in the isosceles right triangle will just be 1. For the secant of 3 pi, we again have to realize that 3 pi will not fall into any of the quadrants, as 3 pi is coterminal with pi radians, or 180 degrees, which lies on the negative x-axis right between quadrants 2 and 3. The reference angle in this case technically is going to be 0, because we are 0 degrees or 0 radians away from the nearest x-axis, because we're right on the negative x-axis. As for the positive and negative signs, both cosine and secant are negative in quadrants 2 and 3. And our terminal side is right between quadrants 2 and 3. So it seems reasonable that the secant should be negative over there. So evaluating this expression, the secant of 3 pi, we could either say that it equals the secant of pi, or the secant of 180 degrees, because it's coterminal with those, or you could say that it will be the negative secant of 0, because we're 0 degrees or 0 radians away from the x-axis, and the secant is negative in quadrants 2 and 3. In either case, this is going to simplify to just -1. Now, just so you know, when we start getting into these things I call mad minutes, the problems that we just did are the types of problems you're going to see. You'll be given 5 problems like the ones that we just did on the previous slide, and you'll be expected to evaluate them without a calculator in 5 minutes. The plan is to set them up as a time quiz to be administered through D2L that will be done during an ORT session. Then we'll go over them afterward. If you want to get some more practice, here's an idea. Perhaps you should pause this video and review these 5 examples for the next 5 minutes, and we'll go over the answers quite shortly. On your mark, get set, go. Pause the video so that you can work on these until you're done. Try to time yourself to see how long your work took. If you forgot to pause the video and you're still working on this, you probably want to pause it now. I'll be turning this and giving the answers back very shortly. All right, here are the answers. The sine of 2 pi over 3. We have a reference angle of pi over 3, or 60 degrees, and it's in quadrant 2, which is positive. So that's going to come out to be square root of 3 over 2. Pi over 6 is in quadrant 1, and the reference angle is 30 degrees, or pi over 6. So the tangent of 30, knowing from our table or our reference angle, is going to be root 3 over 3. Negative 3 pi over 4 falls in quadrant 3. We have a pi over 4 reference angle of 45 degrees. Secant is negative in quadrant 3, which makes the expression come out to be the negative square root of 2. The cosine of 2 pi is essentially the same as the cosine of 0. Cosine of 0 passes through the point 1, 0, so x over r will equal 1. Finally, the cotangent of 7 pi over 2, that's coterminal with 3 pi over 2, or negative pi over 2. Anyway, it's a 90-degree reference angle. The cotangent of 90 degrees is 0, so the cotangent of negative 90 degrees will also be 0. So before we do one of these live, we will have a practice run during an ORT session. I'll also be setting up a Quizlet that can help you practice these on your own. Realistically, as you progress into calculus, you are going to be using these expressions so much that you are going to need to learn to compute them in your head quickly. Knowing these values, as well as you know your addition tables or your multiplication tables, is going to help you do much better in calculus. These may be maddening to try to go through, but they will be worth it. So what if the angle isn't one of the special angles? What if you're asked to evaluate a trig function that isn't coterminal with one of these ones that we've been working with? So the reference angle is not 30, 45, 60, 0, or 90. Then you're going to have to use a calculator to evaluate it. The two things that you need to do is make sure that your calculator is in radian mode and that you use parentheses to properly group your angles. Here are some that you might be asked to do on the homework. Let's pull out the calculator and see how we might compute those. All right, so as I said, when working with these, you do need to make sure that you are in radian mode. Since most of what we've been doing up to this point has been in degree mode, first thing we should do is hit the mode button here, and then we'll switch over from degree mode by moving our cursor until we're on top of the word radian and clicking enter. Then I'm going to press second quit in order to get back to our home screen. To compute the sine of 2 pi over 5, we'll enter it here as sine 2, second function here, there's our pi key right there, divided by 5, and we'll close the parentheses, and we're going to get this, 0.9510565. If I want to compute the tangent of pi over 7, we can enter it like so. I'll say tangent of second function, there's the pi, divided by 7. Close my parentheses, and enter it like so. For the sine of negative 2 pi over 9, we want to make sure we're using the white negative key down here below the number 3 and not the blue minus key. So I'll say sine of negative 2 pi divided by 9. Close my parentheses and we enter it like so, negative 0.64278776. For the cosine of 2 radians, we're just going to type cosine of 2, not cosine of 2 pi, because as we've discussed before, there is a difference between 2 radians and 2 pi radians. Similarly, for tangent of 1.3 radians, we're just going to do this. Again, if we wanted to use the radian symbol to guarantee that we're going to get the correct computation, we can do that. That would be a matter of saying tangent 1.3, and then on the angle menu, which here is second function apps, I'll hit second function angle, and then I can choose the little R, which will force this into radians, whether I'm in degree mode or radian mode. I can also, again, reminder, use that value in the angle menu to force it to do degrees if I wanted. So I'll hit second function apps, and I can choose a little degree sign, and even though I'm in radian mode, it's going to compute the tangent of 1.3 degrees. So here's what these values come out as. So we can use this information to answer our questions like so. When doing this on the homework in WebAssign, be sure to double check how many decimal places WebAssign is going to ask you to keep, whether it's 3 places, 4 places, or 5 places, before submitting your answers. Now we're going to try to do something a little bit different. Suppose you wanted to find the measure of an angle where the terminal side of the angle passes through a known point, but it wasn't necessarily a special triangle. How are we going to do it? Well, the first step is to draw a picture of the angle in standard position. And then, just like some of the other problems we've done, we're going to construct a reference triangle and label the lengths of the 3 sides. Once we know what the 3 side lengths are, we want to set up an equation involving a trigonometric function using one of the positive ratios in the triangle. And that will be important, that we want to use one of the positive ratios. Using a negative ratio in our calculation will cause problems. Once we have this equation, we'll take the inverse trig function on that positive ratio, which will give us the measure of the reference angle alpha. From there, we need to compute the measure of angle theta based on measuring angle alpha from the nearest x-axis. If the angle is in quadrant 1, then alpha and theta are the same. In quadrant 2, we'll take 180 degrees minus the alpha to get the value of theta. In quadrant 3, we'll take 180 degrees plus alpha, and in quadrant 4, we'll take 360 degrees minus alpha. Let's look at a few examples. Suppose the terminal side of angle theta passes through the point -2, -3. Determine the measure of angle theta in both degrees and radians, where your final answer is something between 0 and 360 degrees or between 0 and 2 pi radians. Now, we have actually worked with this example before in section 6.3, but then we were just setting up the values of the trig ratios. We weren't trying to figure out what the angle measure was. But we're going to approach this problem the same way. The first thing we'll do is draw a picture of this angle. Here we have an angle plotted in standard position whose terminal side passes through the point -2, -3. We'll drop a perpendicular to the negative x-axis to form our reference triangle. The angle we're interested in is marked by this red arc here, but in order to find it, we're going to first have to figure out what the measure of the reference angle alpha is here. Let's start labeling the sides. The opposite side we're going to label as y equals -3. The adjacent side is going to be labeled as x equals -2. The hypotenuse r is still unknown, but we can compute it using the Pythagorean theorem, which is x squared plus y squared equals r squared. Substituting in what we know, you'll have -2 squared plus -3 squared equals r squared. Expanding that will give us 4 plus 9 equals r squared, or r squared equals 13, making r equals the square root of 13. As a reminder, r is always going to be positive no matter what quadrant we're in, while x and y could be positive or negative depending upon what quadrant we're in. Since this angle lies in quadrant 3, x and y are both negative, but the r value comes out positive. So let's label our hypotenuse r equals the square root of 13. Now that we've solved for the side lengths of the entire triangle, we could set up equations relating any of the 6 trig ratios, but what I'm going to recommend here is that you use one of the 3 primary trig functions, either sine, cosine, or tangent, and we pick the one that is going to come out positive. Since this angle has its terminal side in quadrant 3, this problem becomes easiest if we use the tangent ratio y over x opposite over adjacent, because that will reduce to a positive value of 3/2. From here, we can take the inverse tangent of 3/2 and we'll get 56.31 degrees. Now, this number, 56.31 degrees, is not our final answer. This is only the measure of reference angle alpha that we've marked in blue on this graph that's being measured off of the closest x-axis, which for us happens to be the negative x-axis. We still have to do some work if we want to find the measure of angle theta, which wraps all the way around from the positive x-axis. Well, because theta's in quadrant 3, we're going to add 180 degrees to the 56.31 degrees to come up with 236.1 degrees as our final answer for angle theta. If we wanted to do this in radians, we actually have a few options. We could first set our calculator into radian mode, take the inverse tangent of 3/2, which will give us a reference angle alpha of 0.98279 radians. And then from here, in order to find the measure of angle theta, instead of adding to 180 degrees, we can add this to pi radians. Decimalizing means taking pi, which is 3.14159, and adding our value of alpha, 0.98279, to get 4.12438 radians. An alternate approach would be just to take the answer that you got in degrees and convert it into radian measures by multiplying by pi over 180. Either process will work, but as we move forward through the course, it will be important that you be able to think in radian measurements. It's like when you're learning a new language. You know you can become fluent when you can start processing things in the foreign language in your head without first having to translate what you heard into English before turning it back into the language that you're learning. Here's another example that we can start together, but then we can pause in the middle to see if you can do this one on your own. Suppose the cosine of angle theta is 3/4 and the terminal side of theta lies in quadrant 4. Determine the measure of angle theta in both degrees and radians. Again, this is an angle that we worked with in the last section. We want to construct our reference triangle in quadrant 4 in such a way that the adjacent side x is going to be 3 and the hypotenuse is going to be 4. The opposite side y is something we'll have to compute later. But in the meanwhile, angle theta that we're interested in is the big angle rotating all the way around from 0 into quadrant 4. But in order to find it, we're going to have to determine the value of angle alpha in this reference triangle. I'm going to pause the video here and let's see if you can figure out how we're going to go on your own. All right, let's apply the Pythagorean theorem and try to evaluate the length of side y. Substituting in what we know, we've got 3 squared plus y squared equals 4 squared, which becomes 9 plus y squared equals 16, or y squared equals 7. Taking the square root of both sides will give you y equals plus or minus the square root of 7. And we're going to make that value negative because we know the terminal side of the angle lies in quadrant 4, and the y values for any point in quadrant 4 are always negative. From here, we want to set up a trigonometric equation to solve. Since we are in quadrant 4, our best bet is to be able to use the cosine because cosine comes out positive in quadrant 4. The cosine of this angle is 3/4, which is given. So the inverse cosine of 3/4 will be approximately 41.41 degrees. So that is our reference angle, which is measured in quadrant 4 as 41.41 degrees below the positive x-axis. To get our measure of angle theta, because our measure of angle theta lies in quadrant 4, we're going to subtract 41.41 degrees from 360 to get 318.59 degrees. If we were doing all of our computations in radians, we would get the inverse cosine of 3/4 equals 0.72273 radians, which we would want to subtract from 2 pi instead of 360 degrees in order to find the measure of angle theta. Decimalizing this gives 2 pi, or 6.28319, minus 0.72273 will simplify as 5.56046 radians. Again, we could have gotten the radian measure by just taking our degree measure and multiplying by pi over 180. That will give you the same answer. Let's try one more. Find the measure of an angle theta between 0 and 2 pi radians where the terminal side of the angle passes through the point 1 half, comma, negative square root of 3 over 2. Before I draw the graph, I'm going to run this through the Pythagorean theorem. Substituting in our values, we're going to get 1 half squared plus negative square root of 3 over 2 squared equals r squared. This becomes, when we square it out, 1/4 plus 3/4, which adds up to 1. So r is going to equal 1. This tells me that the point in question is going to be on the unit circle, which might simplify things a bit. Here's the graph of that situation. What we see here is that the point on the unit circle is in quadrant 4. We have our reference triangle with the opposite being measured back from the point in question back to the positive x-axis. We have the adjacent side, x, as 1 half, and we have the opposite side labeled as the negative square root of 3 over 2. The hypotenuse is going to be 1. The angle we're interested in is this big one, but the reference angle is going to be this acute angle measured from the nearest x-axis. Since we're in quadrant 4, we'll use cosine again to say x over r adjacent over hypotenuse will equal 1 half. Now we could recognize this as one of our special triangles, but if we didn't, we could put this in our calculator for now, and we'll see that the inverse cosine of 1 half would be 60 degrees or pi over 3 radians, and that would be our reference angle alpha. Given that this point is in quadrant 4, we'll take 360 degrees minus the 60 in order to get 300 degrees. Or we could do this in radians and could compute 2 pi minus the reference angle, which will give you 2 pi minus pi over 3, which, if I get common denominators in my fraction, 6/3 pi minus 1/3 pi becomes 5/3 pi. And again, you could just take the 300 degrees that we did the first time and convert it to radian measure by multiplying by pi radians over 180 degrees, as is shown here. So we've arrived at the end of another lecture video, and you're saying, wow, this one is another long one. But in the process, we have covered 2 sections. So this video should be able to get you through both sections 5.1 and 5.2. Both of these problems are actually pretty easy. And a lot of what we have done here is pretty much the same as what we were already doing in section 6.3, except we were dealing with radians instead of degrees. Here are the problem challenges for both of these sections that we're going to be covering in the upcoming ORT session. Be sure to give these problems a try before coming to class so you'll know what to ask for questions, and perhaps you can post some questions out on the discussion board. Thanks for watching, and we'll see you all soon.